This revision video is about Fleming's left-hand rule, which is all about the motor effect, so that's where we're going to start. First thing we need to remember is that if we have a wire with a current flowing through it, we get a magnetic field. There's a small magnetic field. We can find out the direction by using our right hand, point our thumb in the direction of the current, and you can see my fingers are curling on this way, so my magnetic field curls on that way. If I have the wire as part of a circuit, so current is flowing, but I have it surrounded by permanent magnets, I get two magnetic fields. I get a small magnetic field from the current flowing through the wire, but I also have these magnetic fields from the permanent magnets north to south. And what happens is this wire moves, and the wire moves because a force is generated on it, and force is called the motor effect. This movement is called the motor effect. So what happens? First thing, we turn the circuit on, we get a current, so we get a small magnetic field through the wire. And that's surrounded by the permanent magnets. So the small magnetic field interacts with the permanent magnetic field. They interact. Remember, magnetism is a non-contact force, so a force is generated. And when that force is generated, the wire will move. So how do you know which direction that wire is going to move? Well, this is where we use Fleming's left-hand rule. And Fleming's left-hand rule is all about your left hand. So what we do is we have our thumb, our index finger and our middle finger all at right angles to each other. So I'll do my amazing picture here. Thumb, index finger and middle finger, and the other two fingers are not used. And they're all at 90 degrees. They're all perpendicular to each other, all at 90 degrees, and our thumb shows us the force. Our index finger shows the direction of the magnetic field, and that's the magnetic field of the permanent magnets, and our middle finger is the current. And the way you can remember this is FBI. So F for force, magnetic field is B, and current is I, just like in the electricity unit. And we'll come back to why this magnetic field is B in a minute. But anyway, what we do is we have our thumb, our magnetic field and our current at right angles to each other, and we line them up. We line them up, so we line our middle finger with the current, our middle finger with the magnetic field, line it up, and our thumb, the direction of the force will be in the direction of the magnetic field. Key thing to remember is that when we're drawing circuits, current flows conventionally from positive to negative, so that will help you when lining it up with your middle finger. It's more important to be able to explain how to use left-hand rule rather than to actually use it itself. And there's an equation for all higher combined and higher physics students that we need to be able to use, and that tells us the size of the force. And this equation is given on the equation sheet. The equation is force equals magnetic flux. And magnetic flux basically means how strong the magnetic field is. Force equals magnetic flux times current times the length of the wire. And that length of the wire is the length of the wire in between the permanent magnets, not the total length of the wire. Length is in meters, current is in amps, magnetic flux is a new unit, and that's measured in Tesla, which is a capital letter T, and force is in newtons, like it always is. So to increase this force, we can increase the magnetic flux, and that basically means increase the strength of the magnets. If we use stronger permanent magnets, we get a bigger force. The wire will move further, the wire will move faster. If we bring the magnets closer together, we'll increase the strength of the magnetic field. So we're increasing the magnetic flux, we're increasing the force, the wire will move further, the wire will move faster. So if we increase the magnetic flux, we increase the force. If we increase the current, we also increase the force. The wire will move further, the wire will move faster. And if we've got a longer piece of wire in between the magnets, there'll be a greater force as well. And then the last thing we need to know about increasing force is, what about the magnetic flux? Another thing about the magnetic flux. In this picture up here, you can see I've drawn it with a wire at right angles to the magnetic field. That's the most forceful possible. If we have it at an angle, we have our wire going through at an angle between magnetic fields. It's no longer at right angles. It is a weaker force. At right angles it's much stronger. And the direction of this force, the direction can be altered by reversing the current. If we reverse the current, we can swap the power pack the other way around, or swap the battery the other way around. So we can reverse the current to reverse the direction of the magnetic field, the motor effect force. We can also swap the poles of the magnets around. We swap the poles of the magnets around, the magnetic field lines go in the opposite direction, so the force is going to be in the opposite direction, so the motor moves in the opposite direction.